Julian Darden with Lab 2 for Physics 2211. We're studying the motion of a falling object. The purpose of this lab is to observe the motion of, in this case, a soccer ball as it drops straight down. Like last lab, we use Newton's second law, but in this one, it'll be when the net force is not equal to 0. And we will also look at the effects of drag force on the soccer ball. So this is the video I did. I dropped the soccer ball from here, and this give us the graph right here. I'll show you that video analysis right now. I calibrated the video using the soccer ball here, and my y-axis is pointing down here, and then we simply just track the ball. These are the results from the video. Here are all the data points right here. Some of the important calculations that need to be put into the coding would be the ball's mass, the initial velocity, and the 2 times, and the initial position of the ball. Here's a better look at the graph from the experimental version. You can see that the ball increases velocity as the slope increases downwards, and it is going in the y direction. So obviously the net force is 0 because the velocity is changing. So for coding, we put in the ball's mass. For the initial conditions, we have the initial position, which is 0.001 on the y-axis. The initial velocity is a negative 0.275. Initial time is t equals 0. The step size is 0.001, so it's a small step. Gravity constant at 9.8. And my drag constant at 0.212 gave me a good estimation of the final position of the ball. My final time was 0.56, so I've inserted that there. The weight force is inserted here, the drag force here, and the F net is the weight force plus the drag force. Newton's second law is here, and also here to calculate the velocity and the position. In order to show the forces on the computated model, we have done arrow. We have put in arrows to show the forces. So my arrow scale is 0.494 meters per Newton, and you'll be able to see those in the video I'll run for you now. So I'll run my module for you so you can see. The ball travels down with the weight force right here, and then the drag force arrow comes here, and you can see the graph similar to the experimental graph as a increasing slope downwards in the negative direction. Here's the comparison of the experimental model to the computational model. The experimental are these orange dots you see here, and that goes down there. And then the computational model without drag force included is the blue line, and you can see that that's pretty similar here, but then the acceleration increases further and continues to go down, and that's without drag force. But when you add the drag force, you can see it lines up almost perfectly with the experimental value. So it can be concluded that if you don't include the drag force, then it's a pretty inaccurate reading of the acceleration. So drag force is very important in this experiment. So in conclusion, in comparison to the last lab we did, the net force is not equal to 0, so the velocity does change. And that's interesting to see when you plug that into the computational. It's obvious. The drag force has a large effect on the results. You saw that because the gravity without the drag force computational model was different than whenever you put in the drag force, significantly different. If the ball were thrown to begin with and not just released, I feel like the terminal velocity would have been reached sooner, and thus wouldn't have been able to study the acceleration as accurately. So yeah, when the net force is not equal to 0, you can see how the acceleration is not 0, and you can see that on the graph. Thank you.